Dear Amru Ali Obaid, are you ready to present? Okay, the next paper belongs to dear Georgi Shibkonensky. Are you ready to present?
Yes, I'm ready.
Okay. You can start your presentation. You have 10 minutes, please.
The report that I will present is called Accelerometer-Based Fall Detection and Location Tracking System of Elderly. Falls are measured signs of critical states in the elderly who lives independently and can cause serious further injuries. The proposed system is based on an accelerometer, and its main objective is to provide timely medical assistance to an elderly person in event of fall. It uses an efficient algorithm to analyze the input data from the accelerometer and automatically sends the coordinates of the fall location to the caregivers. Methods that are used to design fall detection system are classified into three categories. Image-based method who use several cameras and microcontroller or personal computer to which the images are transferred, processed, and analyzed so that the system can detect fall. The acoustic vibration-based method use acoustic and atmospheric sensors to detect falls of the elderly. The kinematic method is described by some scientists under the name wearable-based sensor method, and it is characterized by the use of the accelerometer and gyroscope to distinguish falls from the elderly activities from the daily activities of the elderly. In the wearable sensor-based methods, the existing fall detection solutions can be classified into two main classes. The first class only analyzes acceleration to detect falls, and second class of solutions, in addition to applying thresholds to the accelerations from the accelerometer and angular velocity from the gyroscope, body orientation is also used. A mobile application for fall detection based on the algorithm analyzing thresholds, accelerations from accelerometers with posture recognition after fall has been developed. Typical fall detection system determine whether falls has occurred by analyzing patterns of human movement using fall detection algorithm based on lower fall threshold and upper fall threshold. The common acceleration vector ACC containing both static and dynamic acceleration components is calculated from the simple data from formula shown on the slide. Figure 1 shows a working example of the fall detection algorithm using upper and lower thresholds of typical fall. In the modern fall detection algorithms, the algorithm further compares difference between maximum and minimum values of specific fall threshold. When the accelerometer is attached to the user and not moving, an average value called current acceleration or baseline is determined. When fall, the accelerometer values change significantly, and the current difference from baseline is defined as current acceleration value minus previous acceleration value. The second fall detection factor is the change in body posture. Because the posture of the body changes after fall, the angle of the device in use should be measured using the tilt angle y from the equation 3. The angle value is used to determine posture to decide whether a person is upright or fallen. The fall detection application adjusts where the accelerometer is mounted and what is its orientation, with two variants of the algorithm possible after conformation its first part. If the accelerometer is positioned on the arm or thigh of the standing canoe, y is from 0 degrees to minus 90 degrees. In this case of a person initially standing and then lying down, the change in tilt angle would reach 90 degrees. Then the upper angle threshold is used, and when it's exceeded, the foul is counted. When the accelerometer is attached to the chest of the standing person and rotated 90 degrees, y becomes 90 degrees. In this, if a person initially stood upright and then lays down, the change in the tilt angle at that position would reach 0 degrees, and then the algorithm use a lower angle threshold. The proposed system uses 3-axis accelerometer, a component of modern smartwatch and some smartphones. In most smartphones, there is a GPS module and portable devices. It can be added. In the smartwatch or portable device do not have one. A connection can be made to the smartphone GPS module. In such case, the module phone serves as a gateway to the internet and tracking device. The fall detection in our system takes place in sensor nodes that include two separate devices, a smartwatch with acceleration sensor and a mobile phone with integrated sensor and positioning module or wireless controller with acceleration sensor. The mobile phone performs the role not only of gateway with the GPS, but also of independent sensor node because contains acceleration sensor. The whole system can also consist of more than two sensor nodes, usually attached to the arm, thigh, or chest of the elderly person. The smartwatch connects to the smartphone via Wi-Fi or Bluetooth connection. External controller with the sensor is connected the same way to the smartphone. Fall detection is done by reading the sensor's external GY521, sensor on the smartphone Huawei P20 Lite, or sensor on Nokia 5.3 and smartwatch Huawei Watch 2. The developed Android application reports the total acceleration vector and angle for pulse recognition from the phones built in the accelerometer of the smartwatch, and the accelerometer of external sensor. If the set thresholds are exceeded, the application sets GPS coordinates of the location in Firebase real-time database. Detected coordinates are visualized using Google Maps API, which provides an easy way to mark drop locations on the map and integrate them into a web page. External testing was conducted with seven volunteers and 2 elderly people aged 65 and 72. The volunteers used the device on the wrist, chest, and thigh and periodically simulated spontaneous falls. A part of the activities of daily living data was recorded by the elderly and the majority of the younger volunteers who aimed to perform different types of falls in activity of daily living. Table 1 shows the sensitivity, specificity, and accuracy for both scenarios when the sensors on the arm or thigh and when the sensor node is attached to the chest of the standing person. In case 1 of the algorithm, the sensitivity is 96%, the specificity is 98%, and the accuracy is 97%. And in case 2, the sensitivity is 94%, the specificity is 96%, and the accuracy is 95%. The results for the two types of equipment generally indicate the excellent performance on the fall detection system. Development system is set to talk automatically Google Maps on the Google Maps the geo-position of the fallen elderly as shown in figure 5. The caregivers and relatives of the elderly person are notified of the fall and the location of the accident on the map via text message or from the web page of the development system. This report presents the design and testing of prototype of fall detection system that use sensor nodes with 3-axial accelerometer, GPS module, Wi-Fi or Bluetooth modules, and smartphone application. From the conducted experiments, it can be concluded that the proposed positioning system fully achieves its main goal to enable provision of the timely medical assistance to an elderly person in event of fall. Thank you for your attention.
Thanks for your presentation. Dear participants, do you have any question about this paper? Okay, thank you again. I wish you success, dear Georgi Konensky. Next paper belongs to dear Theodore Kalushko. Are you ready to present?
Yes, I'm ready.
Okay. You can start your presentation.
Okay, thank you.
You have 10 minutes, please.
Okay, thank you. Is it the screen share now?
Yes.
Okay. Dear colleagues, my name is Theodor Kalushkov, and now I'm going to introduce you our report about fault tolerance smart incubator with IoT control and alerts. Our report presents a smart incubator which provides a combination of high reliability and remote control via cloud application. It allows custom setup and monitoring of temperature, humidity, eggs rotation, and airflow for hatching different birds. The device has ability to send notifications in case of any component failure or serious deviations from the set parameters of the working environment. The selected electronic components for the hardware part are popular and available on the market and are also an optimal choice in terms of price specifications. The prototype is developed for a small number of eggs, but it can be easily reconstructed for industrial needs and bigger productivity. Our motivation to choose IoT and cloud technologies are described on this slide. You may observe them. And advantages list includes possibility for creation of different working profiles for different birds, sending alerts in critical situations, collecting status data, possibilities for sophisticated distributed control, increased reliability, and multiplication of incubators number. This picture shows the elements and relations between them in developed model for the IoT smart incubator application. The cloud part consists of two components, IoT platform and messaging platform. These two platforms can communicate with users' digital devices to send information about the incubation process. The IoT platform needs to supply virtual pins for all data necessary to be stored and observed in the cloud. It should also provide graphical user interface for visualization of values of important parameters and interactive controls for setting values of parameters of the incubation process, such as temperature, humidity, egg diameter, critical minimum temperature, critical maximum temperature, etc. The messaging platform is requisite to provide messaging application for mobile phones where critical values of parameters and alarm messages can be sent to mobile devices to inform the farmers for parameters value and for the eventual problematic situations. Such alarms can be very high temperature, very low humidity, rollers are not working. When responsible persons receive an alarm message, they can react in due time to fix the problem. Otherwise, the problem may exist for a very long time and damage the production. Here you can see two of graphical user interface controls for visualization important values. And some interactive controls for setting values of parameters. In particular implementation of the Smart Incubator, we have chosen Blink IoT platform that provides a mobile application that can be installed in farmers' mobile devices and web application that can be used on a computer. These two applications serve as a control panel for the incubator. In this case, the user do not need control devices on the incubator, such as keyboards, buttons, displays, etc. It provides all needs types of pins and controls. The messaging platform that we have implemented is Telegram. It also provides application for mobile phone where critical values of parameters and alarm messages can be sent to mobile devices to inform the farmers for the parameters value and for eventual problematic situations. When responsible persons receive an alarm message, they can react in due time to fix the problem. Otherwise, the problem, as I said before, can exist for a long time and damage the production. The electrical hardware part of the Smart Incubator includes Node MCU, Wi-Fi controller as one of the most popular and available for such application. It is a good choice also due to its low price and open development environment that it uses. DH22 sensors measure the temperature and humidity inside. Another sensor, stepper encoder, provides control feedback for X rotation. Actuators include humidifier, heaters, fans, lights, and stepper motor for X rollers. RGB LED reports working state of the incubator locally. Low voltage logic controls the power circuit elements via relays, and 5 volts DC power supply powers the controller. The logic of the Smart Incubator program depends on setup plus loop software architecture of ESP8266. This is the chip of the Node MCU. These two main functions contain particular routines that are executed and are listed on the figure. The most administrative of them is manage controlling processes described in details here. It manages 5 administrative processes implemented in the following routines. Control Smart Incubator, executed in every second, checking incubator climate for out-of-range parameters and managing temperature, humidity, rotation effects, and cooling of the eggs. The development of Smart Incubator has been completed and its operation has been tested by a prototype. It has been working as expected. Its main benefits are full control of the IoT platform, easy setting up the values, complete monitoring over the temperature and humidity for a long period of time, satisfying user experience in a process management, and ensuring the incubator by timely messaging to mobile devices. These graphics show a sample of temperature and humidity values for 1 hour of incubator operation. It takes acceptable time for restoring the normal values after drop to a predefined lower limit. In this period, cooling for 20 minutes is fulfilled from 8:22 to 8:42, plus approximately 5 minutes for restoring the values, with temperature of the air outside of 23 degrees Celsius and humidity 80%. During that time, temperature from 38 degrees Celsius comes down to 31.5 degrees, and then it rises again to 48 degrees Celsius for 5 minutes. Respectively, humidity from 53% comes down to 38% for 5 minutes, and then it rises slowly to 53% for the next 20 minutes. As a conclusion, we may say that the realized prototype provides the reliability of the developed theoretical model of a smart incubator. It performs the preset functionalities by confirming the correctness of the developed program algorithms, the selections of sensors, actuators, as well as the circuit of their connection. Thank you for your attention. If you have any questions, I am ready to answer.
Thank you for your presentation. Dear participant, do you have any question about the paper? Okay, no question. Thank you again. I wish you success in your career,
Thank you.
dear Kalishko. Next paper belong to dear Abdullah Dehayap. Are you ready to present? Dear Abdullah Dehayap. Dear Abdullah Dehayap, maybe not online. Dear Marin Zilewski, are you ready to present?
Hello, I am a colleague of Marin Zilewski and I am available to present this paper.
Okay.
Okay, thank you.
You have 10 minutes, please.
Thank you. Hello, everyone. My name is Daniel Slavov, and I will present you a paper named Design of Automated Coffee Machine through Verilog HDL, which is developed together with my colleagues Vladimir Hristov and Marin Zilewski from the Technical University of Sofia, Bulgaria. In this paper, a control algorithm of automated coffee machine is developed and discussed, and on its basis, control program is synthesized and implemented. Then some simulation studies are conducted to check the reliability of the algorithm, and obtained results are discussed. As coffee machines needs to offer a variety of different types of drinks, and also it's necessary to use and upgrade their functionality and the beverages offered. The programmable object allows us to quickly and easily offer such functionality for developing coffee machine control programs, and also to meet the customer needs, save time for development and for subsequent implementation. Our developed control program allows working of automated coffee machine in 6 modes, which number of course can be increased according to the needs. The modes are milk with sugar or without sugar, espresso and cappuccino, respectively with or without sugar. The control algorithm is presented. In each mode, a certain set of processes is performed depending on the selected program. And this process can be placed in a cup in the stand of the machine, adding water, milk, coffee, or sugar, and also putting a stirrer in the cup. At the end of the operation, a completion signal is emitted to indicate that the program is done and the machine turns off. So every program is independent from one another, can be changed or removed. Here is on your right, the model of our system. Some of the input signals include start button, which is pressed by the customer. There is a global clock and reset functionality. The 6 operating modes and their respective timers from T1 to T6. As output variables, we have coffee cup, finish signal, other products like milk, sugar. Then some simulation studies are conducted. This is for the mode of milk with sugar, where after the activation of the start signal, the processes which take place are adding milk. This is determined by the timer T1. Then adding sugar, T2, stirrer, and completion mode. And the second simulation is for espresso with sugar. Here, processes are similar. The difference is that instead of milk, coffee is added. And the third one is cappuccino with sugar. Here, the products include coffee and milk, and there is no water, which is added. All processes are connected with their respective timers, which duration can be changed. As conclusion, should be noted that control algorithm of automated coffee machine is proposed and discussed in this paper. It allows 6 modes of operation. On the basis of the algorithm, a control program is synthesized and implemented with the hardware descriptive language Verilog. Simulations are done, and the results show that the control is successfully synthesized on FPGA platform, which allows to be then implemented in a real production line of coffee machines. Thank you all for your listening.
Thank you for your presentation. Dear participants, do you have any question about this paper? Okay, no question. Thank you again. I wish you success in your career. The next paper belongs to dear Karligash, Ali Beki. Are you ready to present?
Документи, бързо чукам. 3-4.
Hello, colleagues. Yes, I'm here.
Okay. If you are ready, you can start your presentation.
1 minute, please.
Dear Karligash, are you ready to present? Okay.
Hello, everyone.
Please, you have 10 minutes, okay?
10 minutes, okay. The theme of my paper is SOASTIC programmable paradigm of quality control management and multi-agent systems. In this page, this is my abstract. The quality of decision-making in organizational and technical systems under a condition of uncertainty of control agents. A stochastic model for predicting the reliability of control results and decision-making risks under the uncertainty of model agents was developed. The paper proposes a method of aggregating systems, structural uncertainties of the control and measurement process on the example of a robust multi-aspect. A probabilistic model has been developed to assess and predict the reliability of control and decision-making risks under the uncertainty of system agents. The novelty of the proposed models consists in taking into account this statistical nature of normative values. Next. Describes in detail the materials and methods used when conducting the study. The situations you make from different sources must be given and referenced in the references. Stochastic programmable control risk manager principles are a scientific problem. The statistical nature of structural system agents of the control process generates decision-making risks, which are usually divided into the risk of the producer and risk of the consumer. Quantitative assessment and forecasting of these risks is impossible without the use of mathematical tools and computer technologies. There are a number of works that offer approaches to solving these problems. The problems of quantitative assessment and forecasting of risks in the control of decision-making system is becoming extremely relevant in many areas of science and technology. Under the existing circumstances of total digitalization of the economy and social sphere, along with the effective solution of some local management tasks, unforeseen and undesirable challenges and problems appear. Research methods. The quality management of the control process of some complex control and measurement process is considered as functional sub-process measurement compression and of the compression of the measurement value with standards, analysis, and decision-making are studied. In this problem, the control process is considered as a multi-agent systems where agents should be distinguished: agent external environment, agent object of control, agent measurement process, agent standard, agent analysis, agent decision-making system. In this context, agents combine such properties and concepts as software and hardware technologically targets entities. Joint solution of the common problem by system aggregation, inter-agent information exchange, modularity, extensibility, and adaptability, multi-approach, and process of formalizing the functionality of agent systems opens. In this slide, you see the composition is considered when the distribution laws of the standards SB and SN are approximated by normal laws and the controlled parameters as by the Weibull law. Weibull's law, as studies have shown, is not only of the most common among the known laws, but also the most acceptable for modeling process. Weibull's law, a three-parameter law. Many laws, including the normal law, can be considered in some approximation in special cases of this law. Formula for the total number of falsity, rejected control, and measurement solutions from the simple N. The sample size included 200 observations for each age group. In this figure, you see the results of modeling the non-deterministic case of standards where RMB are a function and the relative uncertainty sigma V, and in this axis. To access the adequacy of the theoretical premises to practical results, a computer experiment was carried out. The purpose of the experiment was to study the meteorological indications of the quality of the control process using the example of measuring blood pressure with a device or tonometer. In conclusion, that the results obtained are extremely important when choosing alternatives in the control paradigm. That is what to give preference into the current professional situation, the precision parameters of devices or regulatory regulations. The results obtained can be used as mathematical and ethological support for automated control systems, for organizational and technical systems. This article was performed within the framework of the project of grant funding for fundamental and applied scientific research of young doctoral sciences under the project Young Sciences of the Ministry of Education and Science of the Republic of Kazakhstan for 2022-2024 years. These are my reference, and thank you for your attention.
Thank you for your presentation. Dear participant, do you have any question about the paper? Okay, no question. Thank you again. I wish you success. Next paper belongs to dear Sarvar Makhmudjanov. Are you ready to present? Dear Sarvar Makhmudjanov. Okay. Next paper belongs to Bhupesh Kumar Devangan. Are you ready to present?
Yes. Yeah. Akshay, are you there? Akshay Singh? Am I audible, Akshay?
Yes.
Yes, I am.
Yeah. Okay, great. Akshay, can you please present?
Yes, I am.
Okay. Thank you. Your voice is a bit low. Please make it please high.
Yeah.
Yeah. Thank you. Please go ahead.
You have 10 minutes, please.
Yes,
dear
yes.
Asha.
Is it visible?
Yes.
Hello, everyone.
Yeah,
So,
great.
yeah, here we are presenting the preventive measurement and prediction of COVID-19 and in India through business intelligence tools. So there was a spread of COVID here in the India due to the Wuhan. It came from the Wuhan. So I am starting my presentation here. So we have so in April 2020, it was spread in the part of India. So using the agglomerative clustering, based upon that, we find the pattern in the occurrences of the disease within the different age groups in our country, India. So the spread was based upon the location in the different region. We divided that into the containment zone. So based upon that, here our objective was to find the disease spread based upon the area where it is affecting more and where it is affecting less. So we divided that, and so we find the pattern of the occurrences, and based upon that, we also put the inventory to the hospitals to manage their inventory and employ accordingly. So we solved it using the agglomerative clustering. So it is a bottom up approach where we starts with many small clusters, and after that we merge it into the big clusters. So we are using the dendrogram to visualize the history of groupings and figure out the optimal number of clusters. So apart from this, we also use the straightforward approach to merge it into the closed clusters and update the proximity matrix until one in a single cluster. So the result was based upon the group ages. We here in the green section, we find that the age population were 20 to 24.9%, which was below the 25 years of age. It was less spreading. So the more it was targeting the age group less than 40. So if the person whose age was more than 40 years of age, there was a higher chances of the death rate in those cases. So we define that using our approach based upon the agglomerative clustering. So we divided that data set, and these are the day moving average of confirmed cases in our top 15 states, where out of 28 states, we have the 15 states where it is spreads were very used. We recorded that, and this was the prediction based upon our agglomerative clustering report. So this is we were approximately we were more accurate about our report, that the actual this is the projected data, and here is the actual. So it was a little difference between the projected and the actual one. So it was only due to the approach which we were using. So we also provided the government that we can use this approach and generate the records and leads based upon the 10 to 15 people who were infected. Out of that, 1 to 3 persons were died. So this was the whole approach which we have used. And thank you. If you guys have any questions. Hello.
Yeah,
Thank you
I
for
think,
your presentation.
thank you.
Dear participant, do you have any question about this paper? Okay, no question. Thank you for your presentation. Again, I wish you success in your career.
Thank you.
Dear Akshay. Next paper belongs to dear Hüsam Swadi. Are you ready to present? Dear Hüsam Swadi. Okay. Dear Boris Kostov, are you ready to present? Dear Boris Kostov.
Yes, I'm here. Can you hear me
Okay.
now?
Yes.
Okay. I'm
If you are
starting.
ready, you can start your presentation.
Yes, 1 second. Okay, I suppose you see my screen.
Yes.
I'm going to present my paper, which is implementation of a robot get position quick function to Melfa robots. Melfa robots are Mitsubishi industrial robots. First, I want to introduce you the current paper, where it's represented implementation of the get position quick function, or so-called GPS function, which allows monitoring and responding quickly to the input signals from an external sensor, which enables the accurate robot position data acquisition according to the signal input timing. This function is used for the alignment correction and for the mapping of the workpiece. You see on the figure 1 the used sensors. On figure 2 is the used robot for the test. On figure 3, which is bigger in the paper, you can see the data of the sensors you see on figure 1. The GPS functions allow monitoring and responding quickly to the input signals from an external sensor, which enables the accurate robot position data acquisition according to the signal input timing. The GPS function is used for alignment correction and for mapping of details. Now I will show you how you can connect the so-called sensor to the robot controller. To connect the sensor to the controller, you must connect it to the one of the special inputs of the controller, which is located on the backside of the controller on CN user connector. It's a very easy connector with 23 pins, with 48 pins. The sensor you must connect to the red pins, to the pins which are circled in red. These are the signals, and the 24-volt voltage supplies, you can connect it to the pins which I have colored in yellow. After a connection from the program of the robot, you can check if the signal is input or it's inactive, the signal. Here on this slide, you can see the programs which were created to measure the distance with the GPS function. The first program, which you see here, is the basic program, which only moves the robot, and when the sensor detects something, the robot stops. The second program, it's a program with measuring how much after the sensor has detected the presence of the robot has stopped. And the third program, it's a more accurate measurement based on the speed of the robot and the speed of the current used tool. Finally, in the analysis, after making 19 points of measures, I have measured that the maximum value of robot speed is 2039 millimeters per second. But all sensors and robots and the robot's input have their delay in the response time. The measured delay in the response time of the sensor was about 0.222 milliseconds, and sorry, this is the robot. The measured response time of the sensor is 0.333 meters per second. I have in the final analysis estimated this delays in the signals, and the error which is generated by the speed of the robot and the delay of the signal for the robot is about 0.45 millimeters. For the sensor is 0.68 millimeters. These values have been added to the program. There's some of the values you can see here, and on the video which I will show you, you can see how accurate the robot is stopping after delaying the sensor. Here on this video, you see how the robot stops when the sensor was detected, and after that, the robot is making correction of the position based on the analysis which I have made. Thank you for your attention. And if you have any questions, I'm ready to answer.
Thank you for your presentation. Dear participant, do you have any question about the article? Okay, no question. Thank you again, dear Boris Kostov. I wish you success.
Thank you.
Last paper belong to dear Kamen Hristov.
Here is Vladimir Christov, the first author. I will be
Okay.
present.
Okay, okay, you can start if you are ready.
Just a moment to share screen.
You have 10 minutes, please.
Okay. I will be present the laboratory stand for research of energy characteristics on electric drive with two-direction energy exchange. The problem of reducing the consumption of electrical energy is a fundamental in the technical and economical policy of all developed countries in the world. This is a problem which is organized from a limited resource for electricity production and from wide application of a number of essential consumers of electrical energy and the typical representative, which are electric drive. According to data from International Energy Agency, about 65 to 70% of the produced electrical energy in the world is used by electric drive, and the AC electric drive is approximately 96%. In addition, to increase the percentage of electrical energy used by electrical motor in a trend to recent year to gradually replace the electric motors of car. And the publication in this article is propose a stand for study to energy indicator of frequency regulated of asynchronous electric drive with energy returns. This is the proposed scheme. It has an inverter with two direction of energy analyze, PLC system to control when we have to reverse the electric drive from motor, AC motor and motor volt, which is made to reactive passive fault torque, and encoder. We choose the inverter Mitsubishi FR A741 and multi-measuring instrument Mitsubishi to energy analyzer. Our stand is to nominal power 7.5 kilowatts, and this is the electrical scheme we use in our stand. This is the other scheme, and this is the external view of the stand, and in the inside in the stand to connection with the inverter, energy analyze, PLC control, and remote control. With this stand, we have to study the energy characteristic of asynchronous motor for two-way energy exchange, and the next article, we present the result from the experiment in the this stand. Thank you.
Thank you for your presentation. Dear participant, do you have any question about this paper? Okay, thank you again. I wish you success. Dear Amro Ali Obaid, are you ready to present? Okay. Dear Abdullah Dehab, are you ready to present? Okay. Dear Sorvar Max Mudjano, are you ready to present? Dear Husham Swadi, are you ready to present? Okay. Dear participants, I want to end the session. Thank you for your attending. I wish all participants continued success. Next section of the day, starting at 4 o'clock. Hope to see you at next sessions.
Thank you. Thank you, Professor.
Thank you.